Okay, so the title is Approximate Ideals and K-Theory, and there's four parts of the talk, which the fourth one is currently hidden. So I'll start just by sort of reviewing some very classical material from the Taurus sequence in C-star algebra K-Theory. And there's two theorems based on this. The first one is a kind of vanishing theorem. So what I'll do is talk about what that says and what this thing is. These approximate ideal structures are meant to be a replacement for the ideals that you get in the classical Taurus sequence. Then I'll talk about the second theorem. So this is the Kuhn formula in the sense of Schoffet, who so nice to see us in the audience. So the K-theoretic Kuhn formula, not the KK-theoretic version due to Rosenberg and Schoffet type of thing. And I'll talk about that next. If I've got time, I'll give vague ideas about how the proofs go, but with any luck I won't, so we'll see what happens out. Just to, the kind of meta goal before I start is to bridge this gap that exists. So between ideas in controlled K-theory, I should definitely mention Liang Yu and Oyano over here, who have developed these ideas of controlled K-theory for C-star algebras that arise from a geometric origin and have got fantastic applications to BAM-con type ideas, starting with Liang's work on finite asymptotic dimension in the 90s. And to bridge the gap between that and what I'll call local properties of C-star algebras. I should definitely mention Wilhelm Winter over here. I should mention the work of Zhang Su on the Zhang Su algebra. I should mention many, many other people, probably on both sides, really. But over here on this side, we're looking at the fantastic recent advances in the structure theory of C-star algebras, which are all local properties. They are properties that start in the form for any finite subset of a C-star algebra and any epsilon greater than 0, there is a blah, 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 so that blah, 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 blah happens. And I'm afraid there'll be some of that in the talk. There will be some of the blah, blah, blahing. It has a tendency to get technical, but that's hopefully not too much. So that's the goal. That's in the sort of back of my mind to try and import particularly some of the ideas over here in the non-commutative geometry context, this non-commutative topology over here into sort of more abstract C-star algebra theory. Like Robin's talk last week, this is definitely non-commutative topology, not non-commutative geometry topologies. Okay, so that's the game. I hope that's not going to give anyone motion sickness when I'm zooming in and out constantly. Yell at me if it's annoying. So let's start with the Taurus sequences. So I want to start with A being a C-star algebra. So for simplicity, this is sort of, let's just assume it's commutative. So there it is. X. And C and D are ideals in A, with A being the direct sum. So you can imagine a situation like this, where there's an open set U. Let's do a different color, let's have it green. Here's an open set V, and they are, this one is C0U, and that one is C0V. So this situation corresponds to a cover of the underlying topological space, which may or may not exist, by two open subsets. Okay, that's how we should think of this. And just like in classical algebraic topology, from that you get a six-term exact Taurus sequence, which looks like this. This is basically equivalent for usual and better known six-term exact sequence for an ideal and a quotient. Of course, if you know one, you can deduce the other easily. You could base all of C-star algebra K-theory on this instead. And the maps are kind of the obvious ones. So that one is just given by add. I should really include inclusion morphisms, but I'm sloppy and not bother. And that one is given by just inclusion, but just by sign, I guess, to make it exact. And then there's also this boundary or index type map, which I'll talk about in a moment. It's more complicated to define, but that's what the Taurus sequence associated to two ideals looks like. So the next thing I'll say is how to construct this boundary map partial. And I'll do this in a very concrete way because I won't go into the proofs that much. The explicit formulas are really important for the proofs. When I was young and impressionable, or well, younger and even more impressionable than I am now, I went to a talk by Alan Kahn, as many of us have, at various points. And one of the things he said in terms of philosophy, which I took very seriously, is that, you know, having formulas is better than abstract existence proofs, because you can do things with formulas, and that's. So I'm going to actually give you the formula. Sorry, this is not patronizing for the great experts in this. But here's the formula. How do you construct this index map? So what you do is the following thing. So morally, this doesn't work. But morally, what you do is you find an element H, which is in the center. That Z means center of your C-star algebra. And it's, for one means it's a contraction. The plus means it's positive. With it being in C and 1 minus it being in the other ideals. So again, if I picture this cover situation again, and what would my function H be? Well, if I'd given myself slightly more space to do that, then the function H would be something like that, where that's 1 and that's 0. So it's like a partition of unity subordinate to the cover, and it will have those properties. So in the commutative case, such a thing does exist. In the non-commutative case, it certainly doesn't, but I'll get back to that in a minute. Morally, it does. It almost does. Okay, so that's a picture. That's what this thing should look like. It's like a partition of unity that separates the space or the C-star algebra into 2 bits. And then you're given, oops, wrong pen. And then you're given a class in the K1 group. So that's an invertible element in some matrix algebra, C-star algebra, so GLNA. I use invertibles rather than unitaries. That's, again, important for the proofs in a way that I will sweep under the rug completely. And then here are the formulas. So you have defined an element A like this. So you sort of cut down U to just 1/2 of the space and keep things trivial on the other half. And B, something similar, but U inverse. And then you do this construction using what you might call the Whitehead trick or Whitehead lemma. So you build that thing, which is a nice invertible element, double the matrix sizes. So that's explicit formulas. And then if you feel like just doing some algebra and not paying attention for the rest of the talk, you can have fun checking that these 3 properties here hold. So D is then in the unitization, matrices over the unitization of D. V times this thing is in matrices over the unitization of C. And this difference of idempotence is in matrices over the intersection, C intersect D. Okay, you can check all that stuff. Of course, not hard. Right. And then you get a nice map on K-theory. So it takes a class of this invertible element to this formal difference of idempotence, which makes sense by this condition up here. Okay. And you can check okay, with some work that that doesn't depend on any of the choices involved, and it's well defined and it fits into the exact sequence. And that's all sort of elementary checks that you would very much the sort of thing you would do to check the analogous properties for the classical index map if you look at one of the basic textbooks, like the one by Gordon and Lutz and Larson, or the one by Noncommutative. So you can do all of that. It's all very nice and elementary. So that's a classical Taurus sequence. Okay, right. So here's a sort of key philosophical point. Just pause for a moment. Anyone want to interrupt? Cool. Yeah, it's sort of, we're giving a talk in this setting because I can only see like 5 people at once on my screen. So normally when you're giving a talk, you know, you see the whole audience and you can pick on people who look confused and things like that. But you get feedback from the audience. You can see how it's going. This is a bit different, new experience for us all. Anyway, sorry for the, I have this terrible habit of breaking up my talks to give talks about the process of giving a talk. I'll stop doing that. So anyway, as I said at the start of this page, this thing here where it said morally do this, you can't do that. Okay, the center of a general C-star algebra will quite likely be trivial. So there's no way you can find this partition of unity type element. Okay, exactly, you can't do it exactly. What you can do, just get rid of the word morally, is you can do this approximately, okay? So what you do is, and which you can always do, is you take a quasi-central approximate unit for the first element C, you take some element which is far enough along that quasi-central approximate unit. You won't get this property exactly necessarily, but you'll get it up to a sort of approximation, which is good enough for current purposes. Again, you won't get centrality exactly, but you'll get it up to an approximation, which is good enough to make this work. C-star algebra K-theory is topological K-theory, so doing things up to an approximation is good enough. You won't get honest idempotents necessarily anymore, but you'll get things that are very close to being honest idempotents, and that's all good enough, okay? So the key points, the key takeaway, once you think about how to do this generally, is that you can do this only if you have this data up to an approximation. Don't need it to hold exactly. And once you've done that, you can think, well, okay, hang on, if I can do that, then I don't really need actual honest ideals. I only need things which are locally ideals in some sense. And this is, I guess, one of the motivating ideas behind Guillaume's work in the controlled K-theory setting. So you only need something that's approximately an ideal, and that's good enough. Okay? So then try and think about that and play with that. You can think about what that might mean and how widely such properties are likely to hold. All right, so that's the end of part 1. That's for motivation. So we want to try and get this sort of the Taurus sequence using things that are only approximately ideals. That's my email. Okay, there we go. That's the next page of the talk. Hope there was nothing embarrassing or confidential in there. I don't think there was this morning, so we're safe. Okay, so here's part 2, approximate ideal structures and vanishing. So again, A is just any old C-star algebra, and C is some class of pairs of C-star subalgebras. Okay, not ideals anymore, just any old C-star subalgebras. Okay. And then we get to one of these local properties. It's not quite local, but it's more or less local. So A admits an approximate ideal structure, meaning that you can sort of, what it means is that locally you can find one of these pairs, which is approximately one of these partition of unity type things, as far as that local data is concerned. So what the local data means Let's close that so things stop beeping. What the local data means is that you fix just a finite subset in the C-star algebra, and you fix an error tolerance, epsilon greater than 0. So you look at for all of those. And for that, you can find one of these things which are meant to be like a pair of ideals that add up to the whole thing, meant to be like a couple by open sets. And you can find, again, a positive contraction, so the 1 plus a 4, positive contraction which is positive. The n is for multiplier algebra, ignore that. If you want to pretend the whole thing's unital, then you can. And it should have, whoops, that's not what I meant to do. And it should have the following properties. Okay, so the first one is that the H element should be approximately central. So this says that H is almost central as far as your finite subset is concerned. So that's like the centrality condition that we had before for the element of the partition of unity. Oops, there's a typo there. The second condition is that H should almost multiply things into C. So if H was actually in C and C was actually an ideal, then that would be true. Okay, so this condition here, let's write this down. This condition here is like saying that A is central. Sorry, no, it's not. It's like saying that H is central. This condition here is like saying that H is in C, and this condition here is like saying that 1 minus H is in D. And then you need a profoundly annoying third condition, which would be automatic if they were actually ideals. That's this one. And this is like saying that H times 1 minus H is in C intersect D. Okay, and of course, if H was in C and 1 minus H was in D, that would be automatic, that the product of them is in the intersection. It's got to be in both. That's not automatic. Oh, sorry, I've written this belongs epsilon and explain what that means. What that means is probably the obvious thing. It means that up to epsilon error, it's in the subalgebra. So there is something in the subalgebra which is within epsilon of it. So those are the three conditions. Okay, so it says that locally you can cut your C-star algebra into 2 bits. Right, and if that's going to be interesting, you want examples. So, sorry, it's a bit technical, but hopefully the moral idea is clear. So observation, let's maybe hide the caveats. Due to many people, I should have put more names on this, but at least due to Kirchberg, they didn't prove it for this reason, but things they proved imply this, that Kirchberg is important, and all these people, Johan Boser, Nate Brown, Yazidi Kasato, and Crucius Stuart White and Wilhelm Winter, is that any nuclear C-star algebra, so anything at all, even if it's simple, admits one of these approximate ideal structures where the collection C consists of really nice C-star subalgebras. What does nice means? Nice means matrix, finite direct sums of matrix algebras over commutative C-star algebras with one-dimensional spectrum. So basically, finite direct sums of matrix algebras, except you allow some one-dimensional topology. Okay? So something really, really easy. Right. Now, that's not true. But it's true up to KK equivalence, which if you only care about K theory is fine, of course. Of course, it's strong. But bear in mind, this is for any nuclear C-star algebra with no assumptions, not assuming the UCT, nothing like that, okay? Just nuclearity. So, okay. So up to KK equivalence, a very weak notion of equivalence, but okay, if you only care about K theory, that's fine. And very annoyingly, it's not clear you can get condition-free, and that's important for applications. There are other examples where you can get condition-free. I'll say more about those later. Non-trivial, interesting, even simple examples where there are no non-trivial ideals at all. But it's not clear if you can get this automatically. If you could probably prove some good theorems, but that's to be thought about more later. Okay, so that's the definition of an approximate ideal structure. Whoops, there it is, in full. And at least up to KK equivalence, many, many examples. What I could have said as well, and maybe I will say this, is that if I were to throw in the word simple, I can get rid of this. Okay. So, and then I should add even more names to this part of the list over here. Sam Evington, Jorge Castillos, the other two I would need to add. So if it's simple in nuclear, then this is just true. Okay? So not even up to KK equivalence. So and that's strong, that's quite hard to prove, but these people did prove it, so that's very cool. Okay, right, so that's the condition. Let's talk about some theorems and examples. And again, any comments or questions? Okay, cool. All right. Oh, the condition implies nuclearity, by the way, so nuclearity is necessary to prove that theorem, certainly. Okay. Oh, sorry.
Oh, sorry. So in the previous slide, how did they manufacture the H? It might be very technical. I'm just.
They manufacture the H, so it comes out of it's what they actually proved is very simple nuclear C-star algebra. Oh, I should have thrown in an extra adjective, but let's ignore that. Up to a little bit of fiddling around is nuclear dimension 1. And the H comes from that. Or you could prove it from Jiangsu stability. The H would come from that. It's a bit technical. Yes, that's true. And then you have to prove, the observation is actually something I proved in order to connect their ideas to these ideas. But that's easy. So I'm not really attributing that to myself. You can construct the H out of either, out of nuclear dimension 1, basically. But then I'd have to define nuclear dimension 1, and I don't want to do that, sorry. Partly because I'm doing it by hand, and if I prepared the definition of nuclear dimension 1 in advance, then I could, but it takes forever to write down. Is that okay, Julian?
Yeah.
Yeah. Correct. So morally speaking, that's more or less correct. I should have added an extra adjective, but never mind. This is being recorded, so if mistakes are there forever, let's not worry about it too much. Add errata later, I guess. Okay, so here's an easy observation. This symbol means that C and D are ideals in A. And again, we're going to assume that they're like an open cover, so they add up to the whole thing. And we'll assume that this happens. Then, of course, the K-theory of A is 0 if the K-theory of the, you've got a cover of a topological space by 2 open sets. The 2 open sets and their intersection are all homologically trivial, therefore the whole thing is homologically trivial, of course. That's something that I guess we all know more or less follows from the fact that you have this 6-term exact sequence. That just abbreviates like that, I guess. It's a 6-term exact sequence written as a 3-term exact sequence. So, of course, if any 2 of the groups are 0, then so that's nothing. Just what we're meant to do. And then, so here's a theorem, which is based on work of Eric and Julian and myself. It's the K-theoretic half of something we did. So this is the, let's maybe show the first thing as well. So that's the classical easy observation. And then this is the analog of that for these approximate ideal structures. So say you have one of these approximate ideal structures, and you can do it in such a way that all the things you're decomposing over all your open set analogs are 0. have zero K-theory, sorry, K-theoretically trivial, then the K-theory of the whole thing is trivial. And so if you have one of these local decompositions into things that are K-theoretically trivial, then the whole thing's trivial. And you prove it by proving some sort of approximate Taurus sequence based on ideas of Guillen and of Iono, and also based on ideas in our work with Eric and Guillen on this stuff. So that's a theorem. So application, which is in the work of Eric and Guillen and myself, these two people should have mentioned. This reproves the Baum-Kohn conjecture for group actions of finite dynamical complexity, whatever that is. More precisely, it reproves the K-theoretic half of that theorem in a way which is a bit easier to generalize, which is work in progress with my postdoc. So you do get non-trivial results. You can actually use this to do non-trivial things. It's important that in relevant applications, the classical techniques would, and this is a slight lie, but the classical techniques just wouldn't work. The C-star algebras you're applying this to would often be simple in the applications of interest. So you've got no non-trivial ideals at all. Nonetheless, you can get these kind of Baum-Kohnish results. In that sort of setting, sorry, I should say what the A is. The A would be the cross product, and this applies in many interesting cases where the action is free and minimal, for example, which would give you a simple cross product. So, yeah. So these things do exist in non-trivial ways, and you can get non-trivial results out of them. Okay. So that's the first theorem. Right, okay. So the second theorem needs stronger assumptions. So this is the next bit. So strong, oh, I've forgotten what AIS stands for, approximate ideal structure. Yes, AIS stands for approximate ideal structure and become a formula. So, okay, A is a C-star algebra again, and oops, C is a class of pairs of subalgebras. Okay, so again, think of it as being like an analog. Let's draw the picture again, why not? Think of it as being like an open cover by that one C and that one D by two open sets. Okay. So you should think of these open covers existing approximately and locally. Okie dokie. Right, so strong approximate ideal structure. This is a kind of excisiveness condition. You should say more about that, but I probably won't. And you should compare it to the CIA property of we all know, the CIA property stands for complete intersection approximation, and there's nothing to do with the governmental organization. I assume the pun is intentional, I don't know. So it emits a strong approximate ideal structure if it emits an approximate ideal structure, and you have this kind of uniform excisiveness condition, which is sort of annoying state. But for all epsilon, there exists a delta. That's not scary. So that, and the point is the delta should exist uniformly over all the pairs. That's what makes this annoying. So morally speaking, what this says, ignore the bottom bit, but morally speaking, what this says is that if X is approximately in C and Y is approximately in D, sorry, no, the same X is approximately in D, then there exists, well, maybe a better way to say this actually is just that X is then approximately in both. That's really what this is trying to say, that the epsilon and the delta have to exist independently of the pairs. It's quite a strong condition. Nonetheless, it is satisfied in examples. What it actually says is that I need to the same property, but with an auxiliary C-star algebra. So this is the full group C-star algebra of the free group on infinitely many generators. Sorry. But basically it means that this property happens stably. Okay. Right. It says that if X is almost in C and it's almost in D, then there's something that's almost in the intersection that it's close to, and it's close to the original one, which I could have written slightly simpler thinking about it, but never mind. The C-star F infinity isn't important. It's just something which quotients onto any separable C-star algebra. Okay. Yeah, just that's why. Don't worry about that thing particular, but you need to, that's not what I meant to do, you need to stabilize by that thing. Okay, so it's sort of a slightly annoying technical property, but there you go. Okay, so that's a strong approximate ideal property. It's very much inspired by this thing of A. Okay, so here's recall. This is not an observation anymore. This is a theorem of Claude Choquet from his. Well, no, a definition, sorry, it's a definition of a, sorry, yes, it's the definition of Claude Choquet from his original paper in the early 80s, I guess. So a C-star algebra satisfies a Kuhn formula if for any C-star algebra B at all, there's a canonical short exact sequence that looks like this. Right, okay. So, this is not the same. There's also a KK theoretic thing called the Kuhn formula, which appears in the later paper of Rosenberg and Choquet on the UCT and the Kuhn formula. This is not that. It's not equivalent. It's weaker. But this is the K-theoretic Kuhn formula. And the map, this map here is the obvious external product in K-theory, which is a nice elementary thing. You can think of it as the special case of the Kasparov product, but that's serious overkill. It's elementary. Oh, that's a spatial tensor product, as it is everywhere. So examples in Claude's original paper, Choquet's original paper, he introduced the bootstrap class, I guess, and proved in particular that anything commutative is in there and anything more generally in the bootstrap class satisfies this formula, so satisfies the Kuhn formula. I guess the commutative case is almost due to a T approved it for finite CW complexes, as I remember, way back in the 60s. And Choquet generalized that to general commutative C-star separable, everything is separable. Separable commutative C-star algebras, but also for things in the bootstrap class. And then, okay, a few of these ideas in the paper of Rosenberg and Choquet, anything that satisfies their universal coefficient theorem is KK equivalent to something commutative, therefore KK equivalent to something in the bootstrap class, therefore it will satisfy this too. That's mangling the history slightly, but I don't think I've done anything that's obviously wrong, but I'm very happy they're both in the audience, so please contradict me, Rosenberg or Choquet, if I said anything terrible. Okay, cool. There are, however, satisfying this version of the Kuhn formula is strictly weaker than satisfying the UCT. So very nice papers of Chabert, Epterhoff, Oyono, and Vincent-Lefort. If you have the reduced group C-star algebra of a fairly special group, one with Bollock, property T, and infinite, then fantastic. The clever paper of George Skandalis proved that such a thing does not satisfy the UCT, but these people proved it does satisfy the Kuhn formula. To get this exact statement about not satisfying the UCT, you should look at a paper of Eric Gungner and Nigel Higson, where they proved this precise statement. George proved it first in a more special case for, I think, co-compact lattices in certain Lie groups, but using sort of modern developments in geometric group theory. Eric and Nigel were able to generalize that to this nice, include infinite, this nice general statement. Okay. So Laforgue proved what happened. Laforgue proved that such a thing satisfies BAM-COM with coefficients. These people proved that that implies it satisfies the Kuhn formula, and these people proved that this C-star algebra doesn't satisfy the UCT. That's how the names split up amongst the various bits of that example. So this K-theoretic version of the Kuhn formula is strictly weaker than satisfying the UCT, but nonetheless, it's also not satisfied in general. It implies K-exactness, and that's not true in general. I don't want to say anything more about that unless anyone has questions. There we go. Okay, so that's the Kuhn formula. That's brief background on that. And that leads into the next theorem. Okay. Right. So here's the next example and sort of theorem, I guess. So this is, I've written an observation in scare quotes. This isn't an observation, it's a bit harder, I think, and it's implicit in Schockett's original paper from the early 80s, or at least from the techniques in that paper. But if you have this situation, our favorite situation, where you have a covered by open sets, a C-star algebra that splits into two ideals, and all the three bits satisfy the Kuhn formula, so C, D, and C intersection D satisfy Schockett's Kuhn formula. Then the C-star algebra A also satisfies the Kuhn formula. So that's like a 2 out of 3 lemma. What does appear in Schockett's original paper is the analogous statement 2 out of 3 lemma for an ideal and a quotient. And this is exactly the same idea. We prove it in the same way. I guess the important, I won't say that, but anyway, I can say more if you want. So 2 out of 3 lemma says that if you have these nice things satisfying Kuhn, and the big thing satisfies Kuhn, again, implicitly. It's in Schockett's original 1980s paper. So okay, here's a theorem, and this is very much based on work of Aono and Guliang-Yu. They proved it in this sort of filtered controlled setting, more geometric setting, and this is sort of a local version of the formula. So if you have one of these strong approximate ideal structures over a class of C, forgotten, sorry, forgot the quantifier, that should say full pairs C and D in class C. And all the bits satisfy Kuhn, so that's very much an analog of this observation up here. Then the whole C-star algebra satisfies the Kuhn formula. All right. Now, I will say right now that let's ask this question explicitly. That's the Kuhn formula, which we've already pointed out is strictly weaker than the UCT. It would be great to be able to prove the UCT under similar assumptions. I'm currently in the process of working on that with Guliang, and I think, something like that should be possible, we think, but certainly can't say anything as a result there yet, but yeah, optimistic that maybe this is doable. That would be the thing one actually wants to prove, and start getting bridges between the, again, local structure of C-star algebras and more results on the UCT, which currently is otherwise a very mysterious thing. To get rid of all the scribbles. So again, this does actually have applications, and you can do better than this, but here's a sample application, which is that if you have a group action which satisfies finite decomposition complexity, again, this is a property that was introduced by Eric Guntner, Guliang-Yu, and myself that I mentioned earlier. And annoyingly, you need to assume this. So basically, you're assuming that that's a Cantor set, so X is a Cantor set, which still covers many interesting examples, which you know, the theory of dynamics of discrete groups acting on Cantor sets is certainly an interesting thing. Then this cross product C-star algebra here satisfies the Kuhn formula. This is, right, okay. Now, there are a couple of things I should say about this for the sake of honesty. So that's nice, and it's a nice sort of direct approach to proving Kuhn in that setting. However, it's not new. Finite decomposition complexity applies amenability of the action, and that implies by Jean-Louis Chu's work on the Van-Hong conjecture for amenable groupoids that this thing is actually in the UCT class. So the Kuhn formula is kind of a weak result. So this theorem, this application, I can't claim is particularly exciting from that point of view. That is certainly a more direct proof than Jean-Louis Chu's work, but I can't claim it's new. Jean-Louis has already proved something more stronger. Already proved something stronger. Right. Okay. And you can, however, get new examples because this theorem up here, which is still visible at the top of the page, it's a permanent result. So you can start, how you get the application is you start with compact groupoids, which have very simple, basically subhomogeneous C-star algebras. So type 1 definitely satisfy Kuhn. And then you prove, you start with that class, and then you use this theorem to approximate your original action by such things in some sense, and then you deduce the Kuhn formula. And that's a very simple case because you started with compact things, and the reason such things are amenable is because compact things are amenable, definitely. However, you didn't have to start with compact things. You could start with things that just satisfy the Van-Hong conjecture. And then this closure operation really does give you something new. Okay. So you can get new examples. They're kind of artificial, but it is doable. I've just noticed that my laptop is hard on my laptop. It's hemorrhaging battery while I'm doing this. So I'm going to go and get a power cord, and I will leave you to ponder any questions you might have. Sorry about that. 1 minute. Yeah, sorry about that. I guess, yeah, these kind of video conferencing applications are battery intensive. I was very organized and it was fully charged when I started, almost. Okay, so after that natural pause, are there any questions or comments? I guess, okay. All right, so let me say a tiny amount about the proof. I'll just maybe take 5 minutes on that and leave the rest for questions. Okie dokie. Oh no, revealing secret facts about my current collaborations with Alcides Boost and Siegfried Echterhoff. It's all right. Nothing bad, nothing from students, fortunately. Okay, so there's a very vague idea of the proof. So here's the classical Taurus sequence for a pair of ideals again. And I've numbered, zoom in on that. And I've numbered, there's sort of 3 types of exactness in this exact sequence. I mean, there's really 6 positions in the sequence, 1, 3, 4, 5, 6. There's really 6 types, but of course, up to taking suspensions, there's really only 3 and don't care about taking suspensions. So there's the type of exactness here, and the type of exactness here, and the type of exactness here. Okay. Now, remember that these maps are fairly easy. That one does that, and that one does that. And those two maps make perfectly good sense for any pair of subalgebras. You do not need ideals for those to make sense. Okay? You do for this one to make sense, but in some sense you don't. And that's where the explicit formula that we have right at the start comes in. It sort of makes sense without so many assumptions, sort of locally. Okay. But these two are really nice. They make sense, and the composition is obviously 0 for any pair of subalgebras. What's not true is if you have something here and it goes to 0 over here, that it necessarily comes from there. That you need ideals for, definitely, but the composition being 0 is easy. Right. Okay. And on a sort of meta level, by the way, the fact these formulas are easy is the reason for preferring the Meyer Taurus sequence to the usual 6-term exact sequence associated to a quotient and ideal. Yeah, those you can't get things so nicely because quotients don't exist if you only have approximate ideals, so you have to talk about approximate quotients. And I think it's probably doable, but it would be a mess. I don't want to do that. Okay, so I've got these 3 types of exactness here, here, here. And they're handily covered by traffic lights codes. So the green one is the easiest. The orange amber one is we would say amber in British English. Do you say amber in American English? It's a middle color on a traffic light called orange, probably. The middle one, that's medium difficulty. And then the red one, which is the one that looks like it's probably the simplest, isn't. That one is really hard to prove, and the proof is really vague in a sort of local context, and it's only true in a very weak sense. At least that's all I can know how to prove at the moment. So let's just say a little bit about these 3 types of exactness. Exactness at the first one is just true, sort of. So if you have something in here, and you've got an element in both of these C-star algebras, and it's 0 when you go to, so it goes to 0 in C and in D, then that means that there's a pair of reasons for it being 0, which are 2 invertible elements, which sort of conjugate these 2 things to something trivial. And you can use that pair of invertible elements completely concretely to build an invertible element here. And then you have to think about what this boundary map means, but okay, you can think a bit about that. And you can make enough sense of this that some sort of exactness statement for this kind of triple here makes complete sense. Always true. Okay. Yeah, I have to be a bit careful what this means, but it means you can make sense of it. So that's kind of super nice, and if you prove that first, then you'd be optimistic. The important one for the first application, the Vanishing Theorem, is the orange one. And there you can get some sort of exactness under approximate ideal structure type conditions. So if you have something here, so what does that mean? Start with an element here, then you can take that element, you can find one of these pairs C and D, and also an H, which behaves really well with respect to that element, precisely its matrix entries. Then you can use the H and the concrete formula to construct the boundary map using that element H. Remember, the H was involved in the formula for the boundary map, and this makes perfectly good sense. And then you can prove that if the thing here you have goes to 0 under that boundary map, then in fact it came from over here. Okay? And again, it's completely concrete and elementary. You just try and figure out what the formulas are that when you have that are ideals, and you do a lot of horrible work with epsilons and deltas to make them work approximately, and it all goes. Fabulous. So that's true under those conditions. Exactness, the third position is the hard one, and that you need the strong approximate ideal structure type conditions. And you don't really get an exactness state, some very, very weak exactness statement where it looks like the quantifiers are in completely the wrong order. For it to be useful, I won't write it down. But it looks like it's too weak to be useful. But if you think about how the proofs of the theorems are working, the reason for this strong condition, which is a uniformity condition, is that you can just get the quantifiers in the right order so that the 5-lemma argument for that you want works if you have this strong AIS condition. And then that becomes just enough to prove just enough exactness at that position here. The reason it's the quantifiers in the wrong order is how does the statement work? The statement works like this. It says, say you've got something here in these subalgebras, and it goes to 0 over here. Okay? So if it goes to 0, then there's some reason for it going to 0, some homotopy, which is showing that it's 0. Okay? And what you need for the statement to be true is that this C and D and the H that you get has really good properties with respect to that homotopy. Okay? Now that's in the wrong order because you started with elements over here. You started with the C and the D. The elements went to 0 for some reason, and then the reason is the thing which is telling you how good a cover the C and the D had to be. And that's awful. That looks completely useless, but it's not, because you have to play around with the rest of the proof. But the reason it's not that it's not useless is that you're doing some sort of 5-lemma arguments, and you actually know, you start with something that you know is going to 0 in there for some reason. You know what the reason is in advance, and then you can choose the C and the D based on that. That's sort of what's going on, but it's quite delicate, and that's what makes the paper, which is underlying us, quite long. That key insight is due to the end of A, as I mentioned, but you can really this sort of language as well. So I've got 5 minutes left, so that's probably a good time to stop. Thanks very much, everyone, for listening. I guess I'll stop the screen share if that's okay, unless anyone doesn't want me to. Thank you.
Thank you, Rufus. Do you have any questions or comments?
Oh yeah, I can see everyone again. Cool. Most of you, at least.
Let's reset up code.
Okay. If not, sorry, didn't say that. We'll leave it for.
Can I ask a question? So
Lucas.
So, Lai, do you have a question?
No, just enjoying myself.
Yeah, okay.
So, Rufus, do you have any counterexample for your theorem if we drop the strong assumption in your theorem?
Oh, well, it would depend exactly what it means. No, there is, I mean, it depends what you mean by a counterexample, because you'd need to say exactly what the class C of subalgebras is. But no, we don't. I mean, if I had to guess, what I would guess is that what you can prove, for example, if say you want to prove a Kuhn formula for all simple, for all nucleus C star algebras, say you want to prove the Kuhn formula for all nucleus C star algebras, which everyone would like to prove that, then you can prove that simple nuclear, any nucleus C star algebra is KK equivalent to a simple nucleus C star algebra, so it's good enough to prove it for simple nucleus C star algebras. And then you can prove that they satisfy this sort of structure result in a weak sense, as I mentioned in my previous one of the slides. if you in addition knew that they were one of the nice classes, coming from, if you also knew the UCT, which of course you're not allowed to assume, then modern classification results would would tell you that they're actually k-co-equivalent to one of the nice known models. And the nice known models actually do satisfy the strong version, typically. That's not exactly a theorem because no one has checked the details, but I and people who know more about these things than I do have checked at least enough of the details, but enough of the models. I kind of believe it's quite likely true for all the nice models. So, I mean, it might be true that what you end up proving is some sort of result which says, you know, if you know the UCT, then you know that these really strong structures happen. And in an ideal world, maybe you can even prove that if these strong structural results are true, then you know the UCT. But you would, yeah, that would be kind of my optimistic prognosis at the moment for where this might go. But it doesn't help because you've proved a sort of equivalent formulation of the UCT, but it doesn't, for example. Yeah, but even that's quite an optimistic prognosis, and a lot of that is guesses rather than theorems. Yeah.
Okay, thank you, Rufus. Do we have any other questions?
Yeah, I'd like to ask.
Yes, Claude.
Is there an approximate ideal version of the bootstrap category?
Right, yeah, that's sort of, yes. And that's what's underlying some of these results, that you could definitely prove that. So you could start with, say, you could start with the, say, the normal bootstrap category as your base thing. And then you could say, look at all the C-star algebras which admit a strong approximate ideal structure over the bootstrap category. And then that will give you a new class, which is a priori a bit bigger. And then you could do it again and again and again and again and close it transfinitely. So that would give you a class of C-star algebras. And then it's a theorem, but anything in that class satisfies your Kuhn formula. That follows from some of the things I just said. So you could start with some nice class where you know what the thing you want to prove, the Kuhn formula, for example. Close it under these operations, and that would in principle give you a new class. I think probably provably it gives you, maybe it gives you a new class, maybe it doesn't. And I mean, it might again be that the things satisfying these strong structural properties just are the class of things satisfying the UCT, so who knows if it gives you a new class. Might just be the bootstrap class again. But in principle, it's definitely not. So yeah, you can do something like that, yeah. And that's sort of very much underlying these ideas. This finite decomposition complexity notion that I mentioned of Eric Guliang and myself is very much in that philosophy. As I said, you look at groupoids where if you start with compact subgroupoids, it's not quite right, but morally you start with compact subgroupoids and you close it under some decomposition relation enough times. And you build a sort of bootstrap class of groupoids in that way. No, thank you. I should have said something about that. That's a very good question.
Oh, Rufus, just a small comment. FDC is now used for two different things, which are fairly related.
Oh, sorry, yeah, and I probably even said the wrong thing when I mentioned it.
You mean dynamic?
Yeah, so I mean finite dynamical complexity, and I probably said finite decomposition complexity, didn't I? Yeah, so whoops. Finite decomposition complexity is the original version due to Guliang, Eric Gumner, and Roman Tessera, and then which is a similar sort of idea in a geometric context, and our dynamical version is inspired by and also generalizes that property. Sorry, Guliang, thank you.
No, that's...
Yeah, it's I'm probably going to regret making all these speculations at the end of this is recorded.
Okay, let's thank Rufus again for nice talk.
Thank you.